Hello, I'm Chris Thompson, a NASA Solar System Ambassador from Georgia, and I have a presentation for you on the InSight mission to understand Mars. I put this together using a presentation designed and delivered by Dr. Bruce Bannard of the Jet Propulsion Laboratory, which he used to prepare the NASA Solar System Ambassadors to talk to the public about InSight. I also sprinkled in a few new slides showing some of InSight's launch and recent surface work on Mars. This photo gives you an idea of how big the InSight lander is with respect to the scientists and technicians working on her prior to her launch in May of 2018. Now, planetary missions tend to focus on surface observations, which don't tell us directly about what's inside planets. Most of our detailed knowledge of the interior structure of the Earth comes from seismology, and most of what we know about planetary interiors comes from gravity measurements plus educated guesses about their chemistry. Launched on the anniversary of Alan Shepard's first flight into space, InSight took 6 months to travel to Mars. She carries 3 main instruments and is expected to return data for 1 Martian year, but it is possible the mission could be extended if there's budget money available to support continued operations. This is a pre-launch photo of the InSight lander hiding away inside the fairing of the Atlas V that will boost it toward Mars. And here's the launch over Southern California, the very first interplanetary launch from the west coast of the United States. To give you an idea of how the inner terrestrial planets compare, this view shows the relative size and interior composition, at least the best we know it today. You can think of InSight as a time machine, and its measurement goals travel back in time more than 100 years to terrestrial seismology at the turn of the 20th century. Scientists ask questions like, what's the thickness of the Earth's crust? What's the structure of its mantle? Size and density of its core? And for planets like Mars, they'd ask, how often do Mars quakes occur and how big are they? InSight's science goals travel back in time 4.5 billion years to the very beginnings of our solar system. Science questions like, what were the processes of planetary differentiation that formed the planets? And what were the processes of thermal evolution that modify them? We ask questions about seismology. We want InSight to help us with precision tracking and heat flow. Now, endogenic processes help shape a planet. The interior of a planet holds clues to the processes that formed it, and so we can apply that knowledge to other planets both in and beyond our solar system. Planetary interiors retain the fingerprints of a planet's origins, even though they may be overprinted to some degree by subsequent evolution. In Mars' case, we put InSight on the ground to help us understand the interior of that planet. Mars itself is the Goldilocks planet of the planets shown here. It's between the size of the 2 places we know best, the Earth and the Moon. It will help us understand the formation of terrestrial planets, and scientists will apply that understanding not only to our solar system, but to exoplanets as well. Now, how do rocky planets form? Accretion, or pieces sticking together, grow planets to a large size, but then some things that we don't quite understand yet happen. We know that eventually a planet ends up with a layered composition, a surface crust, a mantle, and a core. InSight is designed to help us fill in the gaps in our knowledge of these processes. The structure of the Earth is relatively well known. The structure of the Moon is less well known, but we do have data for it, and so our models are okay, but not as good as the Earth. Mars was just an approximation before InSight landed, and after a year on the surface, we're getting the data we need to make substantial improvements in our understanding of the planet's interior and enhance our understanding of planetary formation. Now let's take a look at the InSight payload. First, the 3 main investigations are the seismograph, SEIS seismograph, the HP3 heat flow and physical properties probe, and the RISE radio wave experiment, which measures the planet's precession and will help give us an accurate measurement of the core. These ancillary payloads are also found on the main science stack. And there are more than just the three big instruments. These other instruments are out there. And an interesting example to that is the Mars chip, a silicon wafer etched with 2,409,827 names of people like me and my family who signed up on the InSight website before launch. Keep watching for future missions. The Perseverance rover, leaving for Mars in the summer of 2020, just did this program as well. Future missions will give you an opportunity to send your name into space. InSight was originally scheduled to launch in 2016. The delay was caused by a very slight leak in the seismometer housing. The amount of air leaking from the seismometer was the equivalent of your car tire losing 1 pound of pressure in 50 years. Now, it didn't take long to fix the leak once we knew where it was, but it did cause us to miss the initial launch window, which meant we had to wait 2 years and 2 months for the next time the Earth and Mars lined up so we could make the trip. The launch window, that is, the dates during which you can launch from the Earth and successfully reach Mars, occur every 26 months. That window is only about a month long, but the landing date is the same no matter when in the launch window you leave Earth. It is a lot tougher to reach Mars than it is to go into low Earth orbit or go to the Moon, since both Earth and Mars are moving, and you need to plan for all those things that go along during that mission: lighting conditions upon arrival, communications, fuel consumption, and a host of other factors. All InSight's instrument, this experiment is not going as planned. The soil itself is different from what was expected. It's less sticky, so it isn't providing the friction necessary for the heat flow probe mole to dig into Mars. NASA and the German space agency who designed the mole are working on a solution, so stay tuned to see if it works. Here's the mole. It is quite large, about 19 inches long, and it's expected to dig nearly 15 feet into Mars, if we can get it going. Now, the sophisticated radio on InSight will help us determine the wobble in the planet's rotation, which can help us understand the makeup of Mars's core. Taking a look at the mission, you can see here where the InSight lander has come to rest on the Elysium Planitia. It launched at the beginning of its launch window, so it's landed in the orange ellipse labeled open. Landed in that area. And it's in a low area on Mars, which almost all of the planetary probes land in the lower areas, not in the mountains. They need all that room in order to make a safe landing on the surface. Now, surface deployment is key to getting good measurements. And the Viking lander, the instruments to measure earthquake or Marsquakes, were still located on the deck of the lander. With InSight, we're able to get that seismometer right on the surface of Mars, and that will make all the difference. So let's take a look at some real recent pictures. December 19th of 2018, just a month after we landed on Mars, the seismometer was placed on the surface. There's the seismometer, and just a couple months after that, in February, the wind cover was placed over the seismometer to isolate it from the surface, and there our instrument became operational. A short 10 days later, the mole was placed on the surface of Mars, but within a month, we could see that there was a problem. See how the footpads have moved as the mole started digging? The mole housing was then moved so it would allow scientists to see the mole as it is digging and to gain access to the mole to try some other strategies to help it dig. Here's some other pictures of InSight moving the mole structure out of the way to give us access to the mole itself. And here you see the scientists moving the scoop down so that they could pin it up against the side of the mole to help it dig. And you'll see this worked, at least for a little while. You can actually see the mole digging in this set of photos. Now on November 3rd, We found out the good news hadn't lasted for very long. The mole had actually backed out of the hole, and now we're looking at some other solutions, like pushing down on the back of the mole with the scoop. But that's kind of dangerous because the electronic tether you see trailing out of the back cap of the mole is how the power goes into the mole and how the data comes back out. If the scoop damages this sensitive electronic tether, the instrument could be permanently destroyed. In the year since its operation, InSight has found more than 450 seismic signals, the vast majority of which are probably Marsquakes, as opposed to some data noise created by environmental factors like wind. The largest Marsquake was about magnitude 4.0 in size, not quite large enough to travel down below the crust into the planet's lower mantle and core. Those ones would be the best earthquakes to get when it comes to studying the planet's inner structure. But scientists are ready for more. It took months after InSight's landing in November of 2018 before the first seismic event was recorded. But by the end of 2019, the seismometer was detecting about 2 seismic signals a day, suggesting that InSight just happened to touch down at a particularly quiet time. And scientists still have their fingers crossed for getting some larger earthquakes and really probing the interior of Mars. InSight's instruments have also detected thousands of passing whirlwinds and recorded more weather data than any other mission on Mars. We still have nearly a year to go in the Prime mission, and who knows how much more data we can still collect, as long as InSight is operating effectively. Stay tuned to nasa.gov/insight for all the details. Thanks for listening, and I'll have some more videos on other NASA missions soon. Keep your eyes on the skies.